Good afternoon, Senior 2 students. We're still in Chapter 1, Lesson 2, Atomic Emission Spectrum. Heating atoms of pure element in gaseous state to high temperature or exposing them to low pressure inside an electric discharge tube, as in Thomson experiment, they emit radiation called emission spectrum. As you observe here, we have an electric discharge tube, and inside it a gas at low pressure. By applying an electric spark or high voltage in this electric discharge tube, you can observe that light emitted from this tube. By analysis of this light by a device called a spectroscope, it was found that it is composed of limited numbers or restricted colored lines separated by dark areas, as in the figure. We call it line spectrum. At that time, scientists are not able to explain this phenomenon. If you put hydrogen gas in the electric discharge tube and apply the same conditions from the previous slide, you can observe that four colors are formed, which are red, blue-green, and blue-violet, and violet color, with definite wavelengths and frequencies, and they are separated by dark areas, and we call this light the emission spectrum of hydrogen. Bohr's atomic model. The study of the atomic spectra is considered the key which solved the puzzle of the atomic structure. Let's start with Bohr's atomic model and his postulates about the atomic structure. Points that he agreed with Rutherford postulates are: number 1, a positively charged nucleus found at the center of the atom. Number 2, the number of negative electrons equal to the number of positive protons inside the nucleus. Number 3, electrons rotate around the nucleus under the effect of two equal and opposite forces, which are centrifugal force and the attraction force of the nucleus to the electron. Centrifugal force is a force that arises by the particles that rotate with very high speed, and for this reason, the two equal and opposite forces, for this reason, the electron do not fall on the nucleus. The new postulates of Niels Bohr is: electrons orbit the nucleus in a rapid without emission or absorption of any amount of energy, and the atom in this state is called stable atom. As you can observe here, the electrons rotate with very high speed around the nucleus without emission or absorption any energy. Electrons orbit the nucleus in definite allowed energy levels. They can't be found at intermediate distance between two energy levels, where the electron can move from an energy level to another via a complete jumping, means in one step. If an electron wants to move from the ground state to the fourth energy level, for example, it can make it through a complete jump or in one step. Electrons has a definite amount of energy, depend on the distance of its energy level from the nucleus. You can imagine the energy levels as the rungs of the ladder. As we are far from the nucleus, our energy increase. So the first energy level has the lowest amount of energy, and as the radius of energy level, or as the distance of energy level from the nucleus increase, the energy of it increases also. This energy levels expressed by Bohr through an integer numbers called principal quantum numbers. So each energy level has a number which is called quantum number, principal quantum number. When an electron gains an amount of energy called the quantum, it can jump to higher energy level. As you observe here, we have here the electron in the ground state gains energy and jump to higher energy level. After gaining an amount of energy and jumping to higher energy level, the atom in this case is called excited atom. Since the electron in the excited atom is unstable, so it returns back to its original level with emission the same quantity or the same quantum of energy, but in the form of light. And this is the reason for the hydrogen emission spectrum. Atoms absorb different amount of energy. Then they radiate their energies producing spectral lines. And these spectral lines, this color which is formed by the hydrogen atom, indicates the energy levels from which the electrons are transmitted back to the ground state. You can observe here the hydrogen atom absorb an amount of energy and the electron jump from the second energy level to the third, fourth, fifth and sixth energy level. After being excited, they return back to their ground state, emitting the same amount of quantum they have absorbed. So, if you want to jump to higher energy levels, you have to gain a quantum of energy. But when you return back to your original state, you have to lose the same quantum of energy, producing these spectral lines. An important note here, as you transfer from an energy level to higher energy level, then you return back to the lower energy level, electrons form series of electromagnetic radiations which has special names as in the shown figure. The first series, if we are returning back from upper energy levels to the first energy level, in this case we are called Lemon series, okay? And the emission here will be in the form of ultraviolet rays, which are invisible rays. The second series, we are returning back from higher energy level to the second energy level. In this case, the electromagnetic radiations are called Palmer's series, and they emit visible spectrum, so we can observe them or we can see them. In the third case, we are returning back to the third energy level, and this is called Paschen's series, and they are in the form of infrared radiation. And the last one is called Brackett series. We are returning back to the fourth energy level, and in this case also the emitted radiations are infrared radiations. After explaining Bohr's atomic model, let's talk about the advantages and the disadvantages of Bohr's atomic model. Number one, Bohr's atomic model explained the hydrogen spectral lines. He explained to us what are these four spectral lines. Number two, it introduced the idea of quantized energy, so we are able to determine the energy of the electrons in different energy levels. Let's move to the defects of Bohr atomic model. Number one, it is failed to explain the spectrum of any other element, even that of the helium that contains only 2 electrons. Number two, it considered the electron as a negative particle only, and it ignored its wave properties. Number three, it is postulated that it is possible to determine both of the location and the speed of the electron at the same time. But in fact, this is experimentally impossible. Number four, it described the electron as a particle moving in a circular planar orbit, as this figure. Bohr's atomic model is in the form of planar shape with a planar electron rotating in a planar orbit, and this is not correct. Some modifications after that happens on Bohr's atomic model, and we have here a new atomic model called modern atomic theory. Modern atomic theory is divided into three modifications applied on Bohr's atomic model. The first one, the dual nature of electron by de Broglie. De Broglie said that all the previously mentioned theories considered the electron just as a minute negatively charged particle, but all the experimental data showed that the electron has dual nature. Dual nature means has two properties, two characteristics, which are it is a material particle, but it also have wave properties. The second modification is Heisenberg uncertainty principle. Heisenberg concluded that it is impossible to determine both the velocity and the position of an electron at the same time. But we can speak in terms of probability to seem more precise, which means that we have to determine only the speed or the location practically, but the other one or the other term, we can know the probable place to find an electron. If you want to determine the speed, so the place of the electron, we can say that in this place we probably may find an electron. The third modification is the wave mechanical theory of the atom made by Schrödinger. In 1926, an Austrian scientist called Schrödinger applied the idea of Planck, Einstein, de Broglie, and Heisenberg and established the wave mechanical theory of the atom. He managed to derive a wave equation that conclude and describe the electron wave motion in the atom. On solving Schrödinger's equation, we are gonna obtain four numbers which are called quantum numbers. These quantum numbers will help us to determine the allowed energy levels at which the electrons rotate. Define the region of space around the nucleus where it is most probable to find the electron in each energy level. As a result of Schrödinger's work, our concept of the electronic motion around the nucleus has changed. Instead of speaking about the stable circular orbits and the areas between these orbits are being completely forbidden for the electrons, the concept of the electron cloud used to express the region of space around the nucleus. So, in the wave mechanical theory, we have no orbits and no energy level and no electrons moving in definite orbits, but we have something called electron cloud. As you observe in this picture, here is the electron cloud, and the electron cloud is the space around the nucleus, which is probable you can find an electron. But inside this electron cloud, there is something called orbital, and the orbital is a place of high probability to find an electron.